Good morning to all of you. This webinar is actually, you can consider as a part 2 of the webinar I have done on soil plant water relations. Last time I spoke about the thermodynamic concept, how it is applied to this, and then I connected that with the behavior of water in the soil, in the plant, and in the atmosphere. There are a few things which I mentioned there regarding soil textural properties and pressure changes, and also the emission rate, emission pattern of the drip system will find a place in the present webinar as well. Then only you will get a complete idea about the soil plant water relations and how that knowledge is actually used in the drip irrigation design and field application. I hope this presentation is also attended by more engineers because some of the things which will be discussed here is directly relevant to their work, especially of designing drip irrigation for drip irrigation systems for different crops. We have been seeing over a period of last 45 years, at least that's what I saw professionally, the great changes it is happening to the way we apply irrigation water to the crop. Very simple. I mean, I try to summarize this in this slide, and this has been in various presentations before. This shows the way originally irrigation water was applied to the land at the bottom side with no control. Just by breaking the bund, water enters the land prepared for planting, or sometimes even after planting dry seeds in the land, and then the water then enters. There is absolutely no control, and whatever slope is maintained in the field will give the water a flow, and the flow reaches, supposed to reach on the other end of the field and fill it. This is basically we are irrigating land with no control and no amount of water estimations, how much water is required at that time for the crop or at that time for germination if the seed is already put on. There's estimates at all. It is land and just water application. Then science improved, and irrigators found that this is not probably the right way to apply irrigation water, because the flow is always blocked by the ups and downs in the leveling of the soil on the field. So some places you get water not actually reaching. So they started making ridges, that elevated places within the field, and furrows, which are water channels. And these will allow the water to flow through the furrow. Here again, a certain slope has to be maintained from the entry point to the other end of the field. Then only the water flow will take place. And that is sometimes now a technology of a laser leveling has come, and that seems to have improved the water application rates and the water flow rates in the field and water distribution in the field. Laser leveling itself is not a technology for irrigation. It just levels the land at a certain gradient, predetermined gradient, and that gradient will be helping for water, irrigation water to flow. That's it. Then we have drip irrigation. Okay, I purposefully omitted the sprinkler irrigation, which is actually applying water from the from above the canopy or above the soil using sprinklers connected to a lateral pipe, and then connected to a supply line and a appropriate pump. Here in the field, in-field application, probably the next efficient system is actually a drip irrigation, which you can see the drip lines, and wherever the emitters are placed in the drip lines, once the water start moving into the system at a certain pressure, the soil surface will get wet, and then the water will go down in the soil and the profile gets wet. And finally, we have the subsurface irrigation system where the drip lines are are installed below the ground, and so they give wetness to the rhizosphere. That's it. So this is sort of the progress we made in the irrigation technology concerning last 3 or 4 decades. Flooding was always there anyway. So flooding is the only thing we knew about it. People knew about it at that time. Now what happens when we do all these things? Let's say flooding. This is a flood irrigated field, and some crops and rows are coming. And you see, this is the way the water is going to move to different fractions. You get a lot of water moving by wind, the red color wind drift. Then the surface of the water itself, evaporation starts from there. It's not the soil evaporation I'm talking about. It's actually the water directly transfers from its own surface, because the water is above the soil. And then we have infiltration, which goes down, and the deep percolation, sometimes depending upon the soil strata, the lower soil stratas, water can go down into the soil profile. And sometimes laterally from one end of the field to the other or to the next field, we get runoffs. That is physical water actually flowing above ground of the soil and then moving to a place where you don't want it to go. So these red ones are actually, and then evaporation from the surface I mentioned already. These red marked ones are the ones where water is moving away from the soil after application, but this nothing to do with the crop or nothing to do with the crop growth. What is happening is that when such a large volume of water is applied, some part of the water will get into the crop and crop transpires it. Transpiration from the crop, which means the crop is growing, and that part is actually the crop water use. Then there is a component where wherever the field is exposed, even after the standing water comes down to the field level, the soil is exposed and the wetness from the soil get evaporated. That's evaporation from soil surface. So basically crop water use comes only these two green things: evaporation from the soil surface and evaporation, transpiration through the crop or through the canopy of the crop. What has been happening is that in the flow irrigation and even in the furrow irrigation, which we saw previously, the components of water in the red, the water loss from the field in the red, were far higher than the component or the factor or the fraction of the transpiration or the evaporation from the soil surface. In other words, the planned used water become a smaller fraction than the water which goes into either air or deep into the soil or to the next field by the lateral movement or seepage. These volumes have no accounting. People irrigate. Even now, with all the developments in micro irrigation and people start adopting it, majority of the agricultural fields are irrigated with the flow irrigation only. So it's very simple. In order to irrigate a crop which probably requires, let us say, 5 millimeter water a day, we would be applying something like 20 or 50 or 60 millimeter water into that field. And except for this 6 millimeter, the crop is going to use on that day, the rest goes elsewhere. So this is exactly the way water is moving away from the sink source, from the water source to the different sink, wherever it goes and ends up. People say that it is a hydrological cycle. This water which is evaporating will come down in rain. The water which is infiltrating will go and reach, depercolating will reach the borewell or the sources of the aquifers, all that. But I don't think whether that water which is actually going down without use of any energy comes up again so that it can be irrigated. So there is actually a give and take in this, and the give becomes more than the take. In other words, if you are flood irrigating, you are doing a method of irrigation which is not sustainable, because every time you are exhausting a certain volume of irrigation water which you cannot recover. Now that is the time when we are talking about this drum also. You would remember last time also I mentioned. So we had the gravitational water. If you remember that doesn't, that goes into drainage. Is not available to the crop. The available water which is held between field capacity and the permanent water built-in point in the soil, the wetness or the moisture is available, and then there is a small fraction, the metric water, which also is not available. Now, this is the method of irrigation followed the flooding, because even though our objective is to apply this part, I am actually repeating from last times. Even though we have only a smaller fraction of water needs to be applied to the crop, which that fraction which is available to the crop, because we do not have a methodology to only separate out that water and apply. In flooding, what happened? We apply large volume of water. Gravitational water goes, which is the major component, goes in on its own way. It's not available to the crop, and the crop also gets what is available left out after all these losses are there. So this is the case. Now in this scenario is the introduction of drip irrigation, which when properly estimated amount of irrigation water is applied based on the evapotranspiration of that crop at that stage, at that place, at that crop age, at that place, then we can isolate only the available water fraction, which is the ETP, evapotranspiration water, and apply. We don't have to worry about the excess water which is getting into. This is the principle of drip irrigation. Drip irrigation enables us, it's a technology which enables us to apply that amount of water which is available to the crop alone, without excessively bringing water to the ground, which goes by gravitational losses. I repeated this because for further explanations and ideas I'm going to discuss, you would repeat in your mind. Now that's what drip irrigation is, just to know what it is. Then here water again is applied to the field only, but it is not applied as cutting a bunt or cutting furrows. It is applied through conduited tubes or pipes, because it is coming through pipes and coming out of the pipes through emitters which have got a very microscopic holes. It needs to be cleaned. All the suspended impurities in that water has to be filtered. That's why we use filters. And in the process we can also inject fertilizer, we call it fertigation, to apply to the crop once the crop is there and ready to receive the fertilizer. And all other structures, what you see, pump is for pumping bring the water above from the well to the system. The different types of valves are the security valves for the system, so the system doesn't break when the pressure changes. And you have fertilizer injector, then the sand filter and the screen filter. Finally the water comes to the thing. You have to remember this figure throughout my subsequent presentation, because that helps you in understanding what I'm trying to tell you. Now coming to the part where from the submain pipe, where the ball valve starts, is located, it's the starting of the submain pipe, and where the flush valve is connected is the end of the submain pipe. On both sides we have drip lines, and these drip lines are, in this case, to make people understand, it is placed very close to the plants, which is in a row. In each row there is one drip line. This is the conceptual idea. Water has to be uniformly distributed and emitted or applied or dripped at each rhizosphere of each plant, if they are sparsely planted, or a group of plants if in a row if they are closely planted crop like rice or wheat. So the distribution of the lateral lines is a critical thing. That's the discussion of the topic of today. How many distribution lines or the drip lateral lines required for a crop, or let us say required for a width of 1 meter of soil or a width of 5 meter of soil? It wasn't so difficult in the earlier years, because when drip irrigation originally was conceived, they were mainly used for tree crops. So under each tree in a row, there can be 1 or 2 drip lines supplying water. And where there are no trees, there are no drip lines. There's no need for that. It was easy to decide that like that. Again, there are complications. I will come to those complications and answers for that, solutions for that later. But when we started applying drip irrigation technology to closely planted row crops, what they call, like a crop of brinjal, like tomatoes, rice, wheat, these are individual plants are so closely placed and they fill the land. They fill the land in neat and tidy rows. Or randomly, like in a broadcast rice, a field of rice where sowing method was a broadcasting of seeds with no specific order. They fill the ground. In these cases, what happens is that there are plants everywhere or plants in a row but closer, and root system is actually there under the soil throughout the field of that particular crop, along probably with the weeds and all that. Anyway, let's not go into the distinctiveness of a drip line supplying to a particular arrangement of crop became more important and critical when we started using for closely planted row crops than when it was used for distant planted trees or an orchard crop like a mango or a citrus, etc. Here, one may think that it is just a material issue, or it is actually a geometrical issue, or it is an issue which any engineer can solve it. But it is not so. It actually has 3 major components, and the third one, I'll put it the first one, is the cost of the system, the economics. As I go along with the presentation, you will understand that. That's what the main purpose of this presentation. The alignment of drip line vis-a-vis to the crop rows and the soil is very critical because it decides the cost of the system. How many meters of or kilometers of drip lines you are going to use in a hectare land has got a direct bearing on the cost of the system. Then it becomes important. In the original idea about drip irrigation, etc., because it was branded as an expensive system, so people did not even bother about, you have water shortage, you buy a drip system and put it, and the engineers or the commercial person will decide where to put the drip lines. There very little use of science at that time. And many of these people try to use this to make more money, to sell the drip system to a farmer at a higher cost than what a real system in his field, scientifically designed system in his field need. I hope you understand that. So if you can do about a 2000 meter of drip line successfully an acre land, because of other commercial considerations and profit mongering, more plastic was pushed into the ground. The same 2000 is replaced by about 4800 or 5000 meter. These are example figures only. I will come to actual figures as I go along. Because the farmers, especially small farmers in Indian situation, they were not fully aware of how the system works. Why do we need so much tubing? All that, and they have no idea where the soil versus the wetting and the dripper placement and drip line placement, etc. So they just believed the supplier. And this used to be a case. That is why drip irrigation system, the first in the earlier years, I'm talking about 30 years or so back, when we recommend to people to go for drip irrigation, they say it's very costly. And nobody talked about the cost effectiveness about it at that time. So the point I'm coming back to is that the placement of drip line or the alignment of drip lines in the field vis-a-vis the crop geometry is very critical. Number one factor is the economics, the cost of the system, your investment into the system. Number two, the soil type, which we already learned. In certain soils, water will spread more, so you can take the liberty of having 2 drip lines at farther distance, at far away to each other. While in certain soils like sandy soils, the separation or the spreading, lateral spreading of the moisture will be lesser, so you need to put closer to cover the land. And third aspect is actually the wastage of plastics. While you can do an economic size of the drip lateral requirement or the length of requirement, why put extra plastic into the ground and causes problems related to this? So the first point touches the farmer's pocket. The second point touches whether the crop geometry and the irrigation water distribution in the soil actually matches. And the third point touches the environmental load, the plastic load onto the soil. I try to put these two just to give you a perspective of what is going to come. Now, this is again, I'm bringing back from the last production. This is very critical. This knowledge about the soil texture and how moisture moves, how the soil moisture moves within the soil profile of different types of soil textures is very critical. This is the basis in deciding the distance between two drip lines, as well as the distance between two emitters in a lateral. Again, you have the sandy soil on your left hand side, and so you see the picture where within 15 minutes the water reaches 30 centimeter, that's about a foot. Most of the cereals and all have their active roots there, and in about another 40 minutes it reaches to 60 to 90 centimeter, and there is an outer layer which lesser water moves in there, but it reaches, and 24 hours it reaches about 180 meter, which you don't need it. You don't need to get, but within 24 hours water reaches there, which means the drainage part, the percolation part is very high, and that water can never be recovered by the crop because the roots are not there. Then the lateral spread, if you look at it, it's hardly 15 centimeter on either side. You see, from the center where the dripper point is there, 15 centimeter. This has a relevance actually. So basically that 30 centimeter diameter with the center having the dripper is the place where you can plant a crop. You can plant just outside 30 centimeter also, or 15 centimeter on either side. The root system will be, even though at the time of planting they may not get water, seed planting, but once the root system forms they will move to the water part and then you get it. So basically you can do up to 30 centimeter on either side, 15 to 30 centimeter as a planting location on either side. But coming to as clay, clay soil, you have, it will take long time for the water to reach the 180 centimeter, almost 48 hours. But within the first day, what happens is the water spreads. The water spreads something like 45 centimeter on either side, which is very good. The black color, you can see the diameter, which means you are getting 45 plus 40, about 90 centimeter diameter all around the dripper point. You are assured about a wetness when the dripper works, and there you can plant. Now you have a more area of the land surface where seedlings can be planted. In other words, the next drip line can be far away compared to the next drip line in a sandy soil. I think it is very clear now. So this is very scientifically decided factor. It is not a commercial decision. Commercial decision comes later. This is placement of drip lateral depends upon soil texture. In other words, if a farmer is having only very sandy soil, like sometimes in some parts of Ganganagar, Rajasthan and all that district, obviously the drip line has to be closer if he is going for a row crop than the same crop if it is grown on a highly clayey soil, say for example Ahmednagar in Maharashtra, or Nizamabad in Andhra Pradesh, in personally Telangana. These places, what happens is that you can go with the wider spacing of the drip line. Please understand, I am not talking about the crop spacing. Crop spacing is coming as the next step. This is just the drip line spacing so that the moisture uniformity of spread of moisture throughout the field is ensured. Now, this is the classic diagram. You all know in clay you get more spread, which you already spoke about, and the lesser penetration of the moisture. In a sand, you get more penetration but a lesser spread. And in loam, you are somewhere in the typical bulb shape, you are somewhere in between. So this is why to understand the wetting pattern only, our engineers ask the customer to give a soil textural test report. There are other reasons also. For fertigation we use the NPK values and all that in the soil, but the textural report is important to give you an optimum placed drip lines and drippers, and that's the key for successful drip irrigation. This is a case, I won't say from which country it is. Look at that. This is okay, more of a sandy soil, but even here placing so close to drip lines is not necessary. Now this is probably going back to the commercial interest of the supplier and probably the lack of knowledge of the buyer or the grower. You don't need these many drip lines in that stretch of width of land to give a uniformly wet rhizosphere. But this is actually happening. Many places you can see that actually. This is what I said, loading the soil or field with more plastic. Certainly it's not required for a uniform irrigation. Certainly compared to a clay soil, you need more closer drip line in this. I am not denying that. That's a must, but not what you see in the picture. So this directly goes to the cost of the system. So it is very important. Forget about all other aspects. Because it is affecting the cost of the system, overall drip irrigation extension becomes, the technology extension becomes difficult. Look at here. Totally, okay, those soils are not comparable. This is more of a loamy soil. In other words, the clay content is higher than the one. But see with one drip line, how much the water is spreading is very clearly shown. In this case, there is an excess water also applied. I don't deny that. That's why on the sides, water even try to climb into the next, the ridge. But the point is, with one drip line, on either side, you are getting about 35 to 40 centimeter wetness spread. And here, compared to the previous system, the cost will be far less and the soil is not loaded with plastic. But I agree, that was a sandy soil. This is a loam or more clay, loam probably with a more clay loam type of soil, with more clay in that. I understand that actually. But I'm trying to give you the difference. That is why I said even in the first figure, this closeness is not required for lateral. Now for anybody who is new to this technology, it is time to understand that the uniform distribution of soil moisture, I didn't say water, soil moisture in the soil at the rhizosphere place, that's where the roots are distributed, is our objective. And the objective can be met with an optimum placement of drip lateral to lateral spacing and dripper to dripper spacing than a luxurious spacing which we saw in the first one. And this will be obviously cost effective. There are many other things in this. As I go along, it will come. I just want to make the first comparison. Here you see two plants actually. They are not rows. The rows are the opposite direction. So you can see the two plants. Actually, they are chili plants. and they are dug, and you can see the root spread here. It is dug deeper to see how far the root goes. And in another place at a mature stage it has gone. You can see the drip line also, the typical yellow line of the Jain drip line, yellow band on the Jain drip line, and see the root system and see the wetness, how far the wetness is moving. Basically here, this is the best we can get. The drip line is providing water, and because this plant to plant spacing is about 40 centimeter, you can see that it is 40 centimeter. That is why when I took the photo I put a tape there. 40 centimeter on either side of 40 centimeter, edge of the 40 centimeter there is a crop. That's why the root system also you can see. Now in this case, whether the dripper is in the center of the 40 centimeter or there is one dripper each where each plant is standing, is not a matter at all. If it is in the middle of the 40 centimeter or on the near the plant, it doesn't matter, because in this soil moisture is going to spread from the dripper to almost 35 to 40 centimeter on either side, which are the, in other words, the chili plants on either side, irrespective of the placement of the dripper in the drip line, as long as the drip line has got every 40 centimeter dripper, works very well for the soil. Here, why I put this figure to make people understand that many places I heard questions asked by grower, why the drip line is, the dripper of the drip line is not coming close to the plant. In a row crop, it is not required, because in a row crop, you are actually not having point sources. Even though there are many point sources, they join, they coalesce, and you get a band of wetness. So plants can be there and the roots will be in the wetness, in the wet soil. Now their question of asking a dripper per plant in this case is again because of the wrong system supplied by earlier in India. I'm talking about Indian farmer asking this question. Of course, African farmer also asked me this question later. That's a separate thing. In Indian farmer asking this question in the earlier years when we were doing field work was because some other private suppliers or agents of them coming from overseas, they made a belief in the people that every plant, if you have 40 centimeter between two chili plants, there must be a dripper at every plant. Then only you get good crop. That is totally wrong, because they have not considered the soil movement of moisture as well as providing a strip of wet and wherever the drippers are. In this case, if this is a bit more clayey, I would have given 50 centimeter spacing or 60 centimeter spacing, even if the plant is at 40 centimeter spacing. Please understand that. So it is not necessary that in a row crop like chili or tomato or brinjal, you have to have a dripper at every plant, base of every plant, because you are wetting. This is very important. This is again hinges on the idea of the practical idea of cost. I can provide a drip line with every 30 centimeter dripper, but I don't, looking at the soil and the way the moisture is going to move, I made already a decision I don't need it. The more dripper I put in a per unit length of the drip line, the cost again goes up. While I have the idea of helping the farmer and the technology by optimizing the cost, some other people may not have it. They only want to dump more plastic into the ground, either in the form of a drip line or inside dripper at close quarters. And it is that reason they are insisting that there must be a dripper below every plant, which we don't do it. Once you have a strip, moisture wherever it is emitted will join, coalesce with the soil to the depth of the soil to which the roots are. And based on the emission rate, based on the spacing, based on the soil type only, this has been decided. So that once you have a strip wetting, you do not need a dripper at every plant. That's what it shows. Now, we have an issue coming. That's the first time I'm going to bring the crop now. I first brought the soil, now I bring the crop also. Here in the picture, I have shown two types of spreading. You have the plants, the plant to plant spacing is same. It is 2 rows of plant is 1 meter. In both the diagram, right, left and right. What is different is the drip line spacing. The lateral, what we call the lateral pipe. In the picture A, there is a lateral pipe for every row of plant. So which means if you do that, you would end up having 10,000 meter of lateral per hectare. These figures are shown as 8 meter, just exemplify to make you understand, but actually in 1 hectare you need 10,000 meter drip line. Now coming to the right side, it is the same soil type, and you understood you don't need a drip line for every row of the crop, whatever crop it is. You can economize on that. You can give 1 drip line for 2 rows. Put the drip line in the middle of the 2 rows. That's exactly what is done. The lateral pipe is now sitting in between 2 rows. And here you need to cover same number of crop plants and rows. You need to cover only 5,000, and in this case you can see that actually if you clearly look at the picture, the drip line spacing or the crop spacing is, the crop row spacing is 70 centimeter. In other words, you have more number of rows, while in the previous one it was 1 meter. It's different. So even when the crop rows are brought closer from 1 meter to 0.7 meter, that is 100 centimeter to 70 centimeter, your requirement of the drip line for that field to be irrigated successfully uniformly has come down. When you use 2 drip lines, 1 drip line for 2 rows of plants, you come to half, 5,000 meter per hectare. Now this is economics and the use of science of the soil movement of moisture movement in the soil. We are using to the benefit of the farmer, benefit of providing him a system, efficient system, but less costly system. So this is where we look at the crop geometry, we look at the soil first and decide how much water, how much will be the lateral spread of the water. Then we decide what is the row of the crop, row to row distance of the crop the farmer is going to plant. You can even make recommendations to him if he is having doubt. And we do a lot of such recommendations to optimize plant population also. I will come to that later. There are cases like that. Here, for a beginner, what is to be understood is, whilst every row would take about 10,000 meter of drip line per hectare, the moment you do alternate rows, that is a dripper to 2 rows of the plants getting 1 drip line, you halved the drip line requirement. Very simple, but this has to be implemented based on the. Now, all other things which are going to come down is on this principle of optimizing the drip line requirement for a unit area, because this is money. The investment by the farmer is reduced. For example, now I'll show some examples. See, this is from Punjab. You have a typical alluvium type of soil, salami soil basically. and there is certain spread. You can get about 25 to 30 centimeter spread, and the two drip lines, which is relating at 75 centimeter, and the spread from one drip line up to about 35 or 40 will be coalesced with the other drip line. In effect, the entire bed will get uniform distribution, and as you can see, very uniform crop. It is P crop. In the earlier days, the same field would have received at least 3 drip lines, or sometimes in very crazy cases 4 drip lines. Now this is now not possible because these sort of information and science has actually been passed on to the government, and now they are the decide. If it is a subsidy scheme, they decide the lateral to lateral spacing, and to make them change their mind, it takes a long time. We went through that for certain cases, genuine cases. So here, this is the limit of the drip line spacing, but that is enough. You can see the crop growing very well, successfully. Now, alternatively, you come to this. This is a sandy soil. A sandy soil. You see that this I put it to make you understand the spread, the lateral spread of the water. Hardly 10 or 15 centimeter on either side after probably an hour of dripping, and the water would have gone down. I'll show you later in another diagram. See, this is what it is if you look from the other side. This is the typical type of soil where most of the potatoes are grown. See, for example, in UP, Agra and all that. And on a bed you have two drip line. Even then, the 2 drip line moisture spread has not joined together, but they will be slightly more closer. They are more closer below the surface soil. I'll explain that also how it happens. That's the same. You have about 15 centimeter on either side. So totally about the wet diameter is about 30 centimeter onto the ground. 30-35 centimeter, you can measure it. But why I chose this photo is that there is another thing you can see. You can see moisture below the bed. Just look at the side, the furrow, the wetness. By the time the water reaches the on either side of the lateral, to the extent of 15 to 20 centimeter on either side, moisture has already reached more than 50. The height of the bed is about 15 centimeter, more than 15 centimeter down, and water is spreading into the furrow. In this type of soil, this is what happens. More sandy type of soil, sandy loam. So you don't think that with this line I want to complete wet the bed. By the time you wet the bed on either side by running more time, a lot of water will go below the ground and it will not be useful for the crop. That's so. The decision on the irrigation scheduling, or how much time pumping has to be done, or how much time each section valve should be open so that the drip lateral will continue to emit water, depend on the soil type and the stage of the crop. Suppose this is the time just planted potatoes below this ground. So I don't want the water to be going down below 15 centimeter and reaching the furrows. When it reaches the furrow, it means that below the bed you have enough moisture already reaching there. By the time you get about 20 centimeter wetness on this side, you don't want it. Suppose this is after 2.5 months of the potato growth, and this happens, I'm not much worried because roots are there in the soil, will be exhausting that water also. So this is to say, when you take a decision based on the soil type, the lateral to lateral spacing and dripper to dripper spacing and the dripper discharge rate, all three, I clearly explained all in the last webinar. Based on the soil type and the crop plant rows, in your scheduling and the application rate also, you have to intervene and help the farmer to understand it. In any case, the irrigation schedule will be lower amounts in the just germination stage and early stages, and higher amounts when the peak growth comes in. That is true. But that is the total volume. The application rate also have to be understood clearly, so that Here we have to use a lower application rate. In a really theoretical case, if you are totally applying, let us say 4.5 mm water, I would prefer to apply 2.5 mm and 2.25 mm and 2.25 mm at two different times, so that the water going below the soil will be restricted, because there's nothing for the water to be absorbed. But let us not go into that extreme theory parts of it. The point is, the drip line spacing depends not only on the soil type now, it also depends upon the crop rows. Now these three soil type, these three pictures I put it for people to understand what the lateral spread, what's the lower spread, etc. Now this is it. Now here this is actually a diagram you get from Google anyway. The point I am making is that when you have a drip line with the point source, the water, when it is coming, the very surface spread will be slightly less. Let us say 15 centimeter on either side of the sandy soil. But below that surface, when you go, you will see a bulging of the wetting pattern, so that there will be a bit more. So just by restricting to the top surface spread is wrong. You can also go down a bit and find out how far actually the bulb has moved. So if you get about 15, you get about 18 to 19 or even sometimes 20 centimeter in just below the surface, the water spread on either side. And that's a critical information that also then you have to match with the crop row planting. That is the point. So it's just, this picture is actually to show you, forget about all the things written, the wetting bulb and how the shape of the wetting bulb comes in. How the water gets a bit more lateral spread below the surface compared to what is on the surface. For example, you have pineapple here, single row at a very muram type of soil. You can see the stones around. But single drip line is enough for 2 rows. And actually it was planted with a mulch. So to have more water economy and of course weeds and weed control and all that. But the drip line is below the mulching. In a muram type of soil. That is why the picture is chosen. It's a different type of soil. You can see the stones. Here, coming to Rajasthan, Alwar, you have a crop of fennel. 2 rows are planted. It's actually a 80 to 90 centimeters, it's not uniform, 80 to 90 centimeter width for the bed. 1 drip line is enough, even though this is a sandy loam soil. Sandy loam soil. Because if you look at from the drip line to the plant row, there is about 10 centimeter, and that is getting covered even while the plants were small and even at the time of row, you get uniform wetness. So why in this case, if you compare with the first picture I showed you, with the strawberries with so many drip line, a commercial trader would like to give 2 or 3 drip lines for this, or at least 2, because 2 rows of plants they will give 2 drip lines. I don't, because the growth is wet, good, uniform, even with 1 drip line for the soil. This is exactly the optimization, cost optimization, cost material optimization, avoiding extra plastic to the ground and becoming affordable. Now here, this is in Punjab, same thing. The beds are wider. The bed comes about 1 meter wide, wider than the fennel bed we just saw it. But 1 drip line is enough. You have the potatoes on either side of the drip line, and it has now covered. The growth canopy is covered, and very nice. They are growing uniform. You can see there is no height difference, no stress site or anything. And this soil is slightly more clayey than the soil which you saw in the fennel situation. 1 drip line per bed. Here again, if a commercial person, without looking at all these aspects, and if he's allowed to do, because now government has put controls on all these things, if he don't have control, he might give even 3 drip lines. Potato is a very expensive crop, very nice, very high income crop. So why don't you go for 3 drip lines? We never ask that question to any farmer. You may be growing, let us say, the most expensive crop of saffron, but you don't have to unnecessarily load the soil or the land surface with extra drip line and drippers. This has to be followed. Fortunately, all the subsidy schemes follow now, but the government understood more and more about this. They have made some restrictions on the lateral spacing. Now I'm coming to slightly different topic. Even for tree crops, there is a limit of drip line we can use it. Irrigating successfully without any stress. This is done in two places. For a large mango tree, which has got a canopy spreading more than 10 meter, you can have two drip lines kept away from the tree trunk, so that's where the feeding roots are there. In other words, we call it the root canopy. The root canopy which you don't see. You are actually putting the drip lines in such a way that the root system, wherever the feeding roots are maximum in the root canopy, they get water. It is not necessary that the entire land surface below that tree needs to be wetted. It's not necessary. The tree is growing well, yielding. Now this can be done in a slightly different way. This is another method in the second picture I have seen, which we have introduced several years back. Actually, it first introduced the undivided Andhra Pradesh for mango as well as for citrus. We started giving loops so that the loop will contain the drippers, while the carrying line will be plain polytube. So the cost again will become lesser because you are not loading unnecessary number of drippers, and the placement of the loop is critical. You look at the tree canopy above ground and make sure 1 foot inside the canopy you have the loop. 1 foot inside from the edge of the canopy. That's sort of a thumb rule, which if you dig out that place where the drip line is located, remove the drip and dig out, you will see most of the flesh colored new roots are there. They are the water absorbing roots. So here again, it's not necessary from the loop to the trunk, that's entire space need to be wet. No, it's not required. Its water requirement can be met. You can see the tree with the roots can be met by irrigating, and even from the loop, if the water moves on either side of the loop tube, something like a foot each on either, that much wetness would be quite enough. Because all these cases, the amount of irrigation applied is based on the UTP of the crop. As long as that you maintain, there won't be any problem because you are satisfying the UTP of the crop. That's what it is. So here, what one has to understand is that in fact many farmers, when these technologies were in the earlier days, I remember in somewhere in near Visakhapatnam or something, there's some lemon farm, acid lime farm, where we went in and we saw, and the farmers are complaining, sir, the drip line is wetting only this part of the soil, my tree is so big, it's not getting enough water. I said, how do you know that it's not getting water? So we started digging and the place. So when you dig this place, inside of the ring as well as outside of the ring, you will see moisture there. That's all it's required. What he does not say is that wetness spreading into the top surface and going up to the tree trunk. It is not required. In fact, I had the similar thing when I was working in our neighbor country, Pakistan also, where large extent of orchards we have drip irrigated. Citrus orchard and quinoa orchard and mango. Initially they used to ask this question, your system is not giving enough water, because we just replaced their conventional irrigation system. The conventional irrigation system was flooding the basin. There's no basin, but each tree will be given a square shaped area which actually adjoins with the next tree. Basically the field is flooded, and within the basin the water will be standing, and the water up sometime will go down based on the amount of clay and the percolation rate. But it will be slushy and wet whenever you irrigate. That is not happening. In this case, in the citrus, in the quinoa orange, what I have seen is that the surface is remaining dry, and then we dug it out and showed them how the moisture soil is spreading. And that's what UTP irrigation. It's not flood irrigation. And now people started understanding it. Now here again, the point is lateral spacing. These laterals on the mango, for example, should not be closer to the tree trunk because your root system is away from it. So they are very strategically placed so that wherever the absorbing roots do form below the ground are waiting to get water, that's where the laterals are spread. This is the optimum way of placement of lateral. Or have a loop, which again will never wet the entire surface. If the entire surface is wet, he is over irrigating. That's the thing. The farmer is over irrigating. It's not required. But the absorbing roots are getting water. Now, this is an interesting case. Banana irrigation. Now, obviously, banana is one of the most drip irrigated, and people don't even think about growing banana without drip irrigation. Now, you have on the top, it's actually clay soil, even though it's not highly clay, but then moisture spread will be very good. Young planted plants, so the drippers are very close. They have to be close there because the spreading roots have not started moving. They have not started forming and growing. So that's a place. And then you can move as the banana plant grows, by about 6 months time, you can move that drip line to about a foot or 2 feet on either side or on one side. Okay, one side, let us say one side. Now farmers across in Maharashtra especially, they found that because the temperatures are growing very high and the evaporation rate is much higher than the evaporation rate we use for estimating the irrigation schedule, they found that the water entry and the evaporation are not matching. So what we have done with the same water, instead of going through one drip line, is spread into two. And here there is another issue. These farmers, even initially they went with one drip line, and with the bananas the results and high yield and income, they now don't look at investment into drip as a major thing. For them it is a casual thing to make life easy for them. So they then decided this, by the time mature banana comes, one drip line may not be enough, so they try putting two. In a way, scientifically speaking, because the temperatures of these places go to 49s and 46, 49 in the summer, and at that time when the tree is big enough, its evaporative demand is very high. The transpiration demand is very high. So we need to support that. So two drip lines. So there is a reason for that one becoming two. That's the point I'm making it. It is an experience. Farmers found it. We also found it. We also noted this. So you can have two drip lines. And banana being such a high yielding, high income generating crop, that investment is not a load onto him. And now talking about drippers or plastics in the ground. Here the problem is these farmers are using these systems for maybe 12 to 14, sometimes 16 years. So they think about replacing the drip lines. So they are not getting loaded into the ground. The ground, it stays there. And banana being a full 1 year crop and beyond, you do not have any issue with that. So basically, one drip line in early stages, as the comes later, it's an opportunistic thing. You bring in another drip line, but your design, obviously the engineers know that the design would be for the complete flow. You are using only one or a part flow in the early stages, and later use the full flow. That is what this is. This again helps in especially in banana. What happened? The roots are mostly on the surface, very close to the surface. Just like a long hair, they grow onto the surface on either side, so that you can, if you extend the wetting surface or wetting volume of the soil to more and more area, you are getting higher and higher water absorption. There's no wastage here again. That's why in many places, the furrow which you see there, the furrow will remain dry. The furrow will not, in other words, water will not be going down and draining into the furrow. That may happen if we over irrigate without knowing this. Usually in the scheduled irrigation, the furrow will remain dry. Only the bed part where the banana roots are located mostly will get wetted. Now drip lateral to cover the canopy. Banana we already saw that it covers the canopy. Now you see the three things I have shown. One is the ginger crop. It's on a 90 centimeter bed, and then FRO. That one drip line, slightly heavier soil, means clay content is high. So it's not very clayey also, because very clayey soil will be having higher waterlogging and ginger may not even grow well. So you can see very good growth of ginger, and the water spread is uniform. That's why you get uniform growth throughout the entire line on either side. You see that. So this is the ideal case, and this practically ideal case is generated by applying knowledge and removing greed of loading plastic. Because what I'm saying is that if you look at the number of rows of ginger on a bed, according to the old theory, one may try to give 2 drip lines for each of them, which is not required. That's the point. Now, similarly, sunflower, you can see the sunflower. There are 3 rows of sunflower on 1 drip line actually. It's our crop in Ramdal. And then you come down, of course, we already talked about the loop system for citrus. Now, in southern India, especially in Coimbatore and all, a lot of drip irrigation is used for coconuts. Instead of having parallel lines or 2 drip lines, here again they went for a loop. That's what the coconuts is our system. Now, interestingly, coconut roots are very different from citrus roots. They know it's a monocot. So they will having fibrous root system. One above the other just keep forming and remain in the surface. And that part of that will be get wetted, and because the soil is slightly heavier, in this case, you can see the moisture moving towards the tree. The drip line, the main point, the drip line should not be, even it is a linear line, it should not be closer to the trunk. It should be away from the trunk. So beautifully irrigated. So here we are looking at placing the drip line in such a way that as the crop grows, the root canopy and the shoot canopy develops, the entire rhizosphere will get moisture. They will not get excess moisture, they will get moisture from the one single drip line. There is thinking that there are 2 rows. See, the confusion comes in a reverse way. When a commercial person goes to the ground and see there are 3 rows or 4 rows of ginger, he immediately thinks that there should be 4 rows or 3 rows of drip line. That is what I'm questioning. That is not the case. The case is, in that case also, based on the lateral spreading distance, you can end up giving 1 drip line for 3 rows or 4 rows. That's the point. Now, this is another interesting thing. In India, whole of India, whether it is Maharashtra, Gujarat, and even Tamil Nadu, we usually grow large branched, tall cotton varieties, and we grow single row of cotton, and initially it is 1 drip line per row, and that's the case if you go through Maharashtra, Gujarat, even North Karnataka, Tamil Nadu also. But I have seen in another place, in a neighbor country, where we made beds, and there are 2 rows of cotton on either side of the bed, edge of the bed, and then you have 1 drip line. So there is more economy brought in there. So it's also possible. Now, if you're looking at the left hand up picture, in that soil, if you put 1 drip line in the center, initial period of the first 2 months of the cotton, because cotton roots are not surface spreading roots, they are deep percolating, deep growing roots. They may not get moisture. That's the truth in that Moram type of soil which you saw. But if you have the soil is a bit more clayey, you can grow these 2 rows on 1 drip line. It's also possible. Anyway, it's not tested yet in this type of soils. But certainly on that left hand picture, it's not possible, because for the first 2 months, they will not get sufficient moisture. The more clay is there in the field, and then it is possible. The lesser the clay and the more Moram stony type of soil, cotton is quite happy to grow in such type soil, but then the moisture spread will be. So giving 1 drip line in this case is the requirement there, because of the rooting nature of the crop and the growth rate and the soil type. That's the point. Even this, we could test it out, and that's what the lower picture shows that. In a slightly different type of soil, where you have more of a clay loam type of soil, it's a more loam compared to the other two, and less stones and all that, you can put one drip line and two things. So this is, you will make the decision based on the nature of growth, the rate of growth of the crop, the root spread of the crop, as well as the soil type. So one cannot say one is right, one is wrong. In this case, this is a system which can supply. The main problem is this, not even the soil. Main problem is in the initial stage of the growth, the root system is not spreading laterally more, it's going deeper, so that it cannot get into the moisture zone if you put one drip lateral. That's the point. Now, crop geometry plays a drip line economy. Actually, we have done this quite a lot of these studies when we were getting into drip irrigating sugarcane. So that's about a story about 22 years or so now. Ideally, sugarcane was originally planted by farmers at 3 feet in Tamil Nadu and all that, Tamil Nadu, Andhra and all that. And as you go to the north, you get 2.5 feet. Very close planting. And that remained as a steadfast technology. So that's what, if you have 0.9 meter row spacing, you need 11,500 meter drip line. If you do 1.2 meter, it comes down. Here, drip line spacement is, or lateral spacing, is actually directly connected with the row distance of the crop. That is in sugarcane. As we go along, we will see the differences. Now, it is in sugarcane spacing or crop geometry, a lot of changes could be done by us by looking at the crop, and then it helped in the more and more economic type of drip line placement. That is the first thing to say, evaluation of paired row planting. That is a gift from drip irrigation technology. Why is so? It is because of optimizing drip irrigation requirement, drip line requirement, paired row is thought of. Later, there are farmers who liked paired row so much because the yield increase. There's another reason, physiological reason. They like to have paired row without a drip. They went for that, even for furrow irrigated or sprinkler irrigated sugarcane, they went for. That is the essence of the story which happened. Now let us look at it. With the introduction of drip irrigation, precise application of water to the right place, the right time, right quantity became a reality. That we all know it. This enabled defining water spread area and thus helped necessary space between the two root spheres adjacent plants in a row. Because the adjacent plants, in case of sugarcane for example, their root system will get mingled. So you will get a steady presence of roots throughout the entire length of the field, for the row with the next row, for the plant with the next plant. In this case again, if I take you back to the idea of you don't need a dripper at every hill or every cluster of sugarcane stems, which is called a hill. If you have more tillers, you get more numbers of stem in that hill. You don't need that because the root system is spread throughout. So anywhere in the line, if the water is spreading, roots will get it. And departing from the traditional practice of irrigation, but in terms of irrigation channel, I'll show you that picture also in the next. For each row, you need to apply water in each furrow. But there are cases of alternate furrow irrigation. Later it was tried and all that, but it didn't pick up much speed or much adoption. And in such cases, what happens is that every furrow you have to irrigate. Now, it is in that sort of traditional scenario, with the drip irrigation, we could enter and make a lot of changes. Paired row planting evolved as a relatively new technology for planting, and the main purpose is to optimize the quantum of lateral pipe in the field. The lateral spread of the wetting bulb from an emitter in each soil type is considered as the basis. along with the canopy of the crop. The two things, the lateral spread of the wetting bulb on the surface plus the canopy of the crop. These two considerations is helped in bringing the paired row technology. Two plant rows, a pair, are planted on either side with the drip line so that both the root spheres are within the wetting spread. That's the first point. In addition to higher yield over single row planting, there are a number of advantages in this method, like higher plant population than single row planting, lesser expenses on drip lateral, yes, that's more important, more exposure of plants to sunlight. That's why the yield has gone up in paired row compared to the 2.5 feet single row. And good air circulation in the field, which also brings down, helping to the productivity, diseases, etc. will be less. Now that's what this is. Here what you see, a paired row is that the two rows of cane which are closer, which is 75 centimeter apart, which are, in other words, then you have a lateral in the middle. So lateral to the first row is 37.5 centimeter and 37.5 centimeter on the other side, which is actually 2.5 feet. Yes. So here the two row acted as a unit per lateral. Okay, and the laterals can be 195 centimeter if the pair to pair is 120. But there are many places pair to pair you can increase based on the soil type and the productivity of the soil, which has been done. So paired row cuts down this, so you usually write it as 0.75 into 1.2 into 0.75. 1.2 meter is the gap between the non-planted gap between the two rows, two pairs of rows. And 0.75 is the gap between two rows in a pair, and the lateral 195 in this case. So this is the introduction of paired row and the matching of the drip lateral spacing in such a way that you could bring in economy of the crop system. This is it. The case. This is the actual case. You can see the wetness also. The drip wets about 2.5 feet. On the either side of the 2.5 feet is the two rows of cane sets already planted, and the 4 feet in the center remains dry. This is precisely irrigated at that time. Paired row system. That's what it is. You can see the drip line in the middle of that. It's a different field, but then you can see how the uniformity is growing. But this is the thing we made change to. Every row must have water on either side. This is slightly heavier soil. Possibly, in this case, alternate row wetting also can help. But even that is a lot of water being used. That means one row with water, one furrow with water, next furrow without water. Because roots are there, they'll absorb the water anyway. That's also tried in several crops as a economy of water saving method. But in this is the regular way farmers do grow. So that's what we change it. And you see how uneven the growth is also. Economy of optimizing drip line. Now when we do that, in the conventional single row planting, it is 0.9 meter. That is, the row to row will be 0.9 meter. You get a lateral length for every row is 1250 meter per hectare, and if you do skip row, that is one row there is a drip line, in the next row you don't give. In that case, if you do skip row, just like I talked about the furrow irrigation, skip furrow, here skip row dripper, drip line is only on the number 1, number 2 is not, number 3 will have a drip line, like that. You still have 5625 meter per hectare laterals to be used. But the same field, if you convert into paired row planting, which is 0.75, 1.5 in this case, and 0.75 meter, 1.5 is that wide gap between two pairs, and 0.75 is actually the space between two rows in the pair, in each pair. The lateral length will be 4500 meter per hectare. So the 4500 meter per hectare is much shorter than, smaller than, lower than the single row. In a paired row with the 0.75, 1.5, 0.75, you use only 4,500 meter of lateral. Even in a single row, it will be 1100, that is 11,250 meter. But in the same case, 0.9 meter row, if you do skip row, you still use higher, 5625 meter. So saving in lateral, if you are doing every row, it's about 6,750 meter lateral you are saving. That's a lot of cost actually. Lateral cost comes about 70% of the drip system on an average. That's what the engineers tells me. So you are actually halving that 70% cost, halving, making it 50%, half. In comparison to skip row, it is about 1,125 meter. This is very important for optimizing the plastic required. That will optimize the cost also. And this all happened. This has been now, people have moved out of this also. It becomes so common. There is very little single row planting in, I know in states of Andhra Pradesh, Karnataka, Tamil Nadu, Maharashtra and all that. If it is surface drip, it's always paired row. If it is subsurface, then we will give them a place, either a paired row or it's a single row based on the harvest. We will come to know about that later. So this is where an intervention because of the drip irrigation technology has helped in changing crop geometry. That's the point here. You, instead of adjusting drip lines to crop geometry, here drip line alignment has helped in improving the crop geometry, because what happened was from 0.9 meter row to row spacing, when you went into paired row, yield increased. So basically that 2.5 feet or 3 feet, which is 90 centimeter, 0.9 meter, the 3 feet was actually a wrong thing practiced by several years in sugarcane agronomy. Unfortunately, a lot of research went in the public system, but I think very few people really clearly looked into that crop geometry part. That's surprising thing to people. And we looked into it because we want to optimize the cost of drip line spacing, drip system and drip line spacing. And it clicked very well there. The paired row planting geometry gave higher yield. Now there is another issue. In certain cases where plant population became lesser than optimum, it's not by virtue of the farmers did not know the plant population. He is restricted. Now look at the picture on the left hand side, the top picture. There is maize plants. The drip line is at 1.4 meter. This is the 1.4 meter is decided in a large project. This is actually from Ramdal project in Karnataka, because government has decided, or the project expert who wrote the project did not probably give much importance to the moisture spread of the land and the soil type. I think they hardly considered the soil type, soil texture while deciding the laterals. They only considered equity. That is, if you give this spacing, as you can see in the picture, you can cover more land area, which means more farmers will get benefit. You understand that? It's a community project. But here they sacrifice the certain agronomically important principles, and that created a huge issue there. And we try to solve that issue also. Now look at that, how this is done. When the farmer does that, only 2 rows on either side, because he cannot have a 4 rows, 2 more rows. There are 2 restrictions here. Please understand. You may ask me otherwise. First restriction is the spacing given by the government. That has to be followed. The second is, that's a more difficult thing, the amount of water distributed to each farmer in the rainy season time, when this maize is grown, it's only 2.5 millimeter. You understand this? 2.5 millimeter, that much volume only he will get. So even if I want to tell him, you increase the time of irrigation, time of dripping, so that you can get a wider lateral spread and can accommodate 4 rows of maize to increase the population, because this is the maize population is very low, 88,000 plants per hectare. That's what on the top, and that's not going to give him a very high yield. Whatever fertilizer, all that management you do, because for maize, population is the one critical thing for deciding yield. In a normal case, what would happen if it is a rain-fed crop? Anyway, he has no other way to irrigate. That's why I mentioned this gap between the two sets of 2 rows. He will fill with the equal distance of maize, so that the field will be full of maize plants. But they will suffer, because if the rain is poor, they cannot be irrigated. With the irrigation arriving at his place, the best irrigation system, still he had the limitation, because the water amount given is rationed. The drip line to drip line placement is also in a way rationed. Now these are the 2 limitations. This was put into our head, and we have to produce more yield for maize with the drip irrigation, otherwise he will throw away the technology. You see, so what we have done is, in fact, I spent about 1 or 2 months on this, studying the soil, looking at the crop and all that. Instead of 2 rows, we asked him to plant 3 rows per lateral. The spread will be the same. The spread we measured also, that even otherwise this type of soil is Moran type of soil on top, mostly. You get only 15 centimeter on either side. Maximum spread after the allotted water falls through the dripper, you get a lateral spread only 15 centimeter. In other words, within 30 centimeter, you have to grow maize spreading. That's much water will spread. Though the land is there beyond that you can see between the 2 rows. So we use that, but to our trial, what we have done, we have showed the farmers, instead of 2 rows, you plant 1 more row. So the central row will be right on the lateral, and on either side 15 centimeter away you get 2 rows. So you could add 88,000 plants, you change to 132,000 plants. This is probably the best you can do in this situation. This is a case where lateral spacing, for economic reason and the reason of equity in the society, it is already decided. Similarly, the water volumes that can be delivered is also decided, and it is a deficit quantity of 2.5 millimeter only you will get. In other words, per hectare he will get 25,000 liter water only. Maybe in the early season you don't need that, but the point is that cuts away most of the land surface from getting wet. That's the point. Because the land surface getting wet is limited, number of plants can be planted, rows of maize can be planted. Maize is an example anyway, is also limited. I hope people understood that. So here, one way to partially to save the situation and have lesser yield loss, because the population is less, we introduced 3 rows. And it's a very interesting case actually, and we could get very high yields compared to the normal growing maize, and also the non-drip maize, which is good. You can see the crop is good, uniform and all that. So with the limitation of the wetting spread, we increase the population. That is what happened. So these type of decisions are required, and this requires obviously an expert analyzing the situation, studying the soil, studying the crops requirement, the root system, where it goes and all that, and then make a decision. This is a classic case of that. Another interesting thing is that it's actually changing. This is, I have used this onion case many places to explain many things actually. The left hand side is the conventional irrigation system, that the flow irrigation and onion being planted on either side of the ridge, which is the like your nose bridge is a very narrow bridge, ridge which you can see, and the right hand side is that single drip line on a bed of 1 meter having so many lakhs of plants. When the irrigation type changed, not only more onion could be planted, it released more land. That's what it is. You can read it. When micro irrigation, when adopted, provides opportunities for some well-defined changes in the way we do farming. Here, water is not allowed to flow through channels. The very idea that field channels are not a requisite it has released a lot of unplanted portion of the land for cropping. That's what happened in the second case. If you see, the so-called places where water would have been flowing is also planted with the onion plants, because moisture is made available to the crop by the wet soil, not flowing water. For instance, conventionally 2/3 of the total land area will, and we measured actually, 2/3 of the land area will occupy water channels, and only 1/3 area will have onion plants standing. You see? As a result, we increased the population of onion from 67,000 per acre to 2.5 lakh plants per acre. So you get more yield, obviously, and better use of the land, and long-term sustainability of the land. You are not flowing water and then creating all excess water related issues. And the farmer will get more income. He's happy about that. This is a field research in several onion growing areas, and the rest is history. The farmers understood the value of this type of change. Here, crop spacing changed, population changed, that's geometry changed, and just by utilizing the land which otherwise would have used for only flowing water. Again, why I'm putting this slide is also to show alignment of drip line. If the same drip line, the picture on the right hand side, we study it from one drip line, about 45 centimeter to 50 centimeter water can be spread. That is why the place could be filled with onion plants. And that spreading of the water in that particular soil is a property of the soil. And that property of the soil helped us in increasing or in changing the crop geometry. And when we change the crop geometry, the population changed for more yield, for a lesser, much lesser use of water than the left-hand side picture. Now, we have by studying on different crops, we came to the crop geometry of tomato, for example, 40, 75, 40, 20 paired row. Potato also 40, 75, 40, 20 paired row. 40 centimeter between two rows, the two rows in a pair, 75 the unplanted space, then 20 between the two plants in a row. That's how you have to read it. And the yield increase has 50 to 60%. Water, of course, I'm not even talking about water saving. We all know it is drip irrigated, it is water saving is there. Let us look at the yield increase. The population changed. In some cases, population decreased when you do pair compared to single row 9. But that doesn't matter. Individual plants started producing more because they got more sunlight. They got more area of soil for exploration of nutrients and water. Very simple. And there's no shading. So they gave higher yield. Potatoes, 20 to 30% yield. Brinjal, 75-20 is a single row in a drip line. So 20 to 30 because it has got a flat umbrella type of canopy. You cannot accommodate too close. Chili, you have cauliflower. Cauliflower is one interesting crop. Usually it used to be one row and next row like that. Here we made it into paired row. 80% increase. Cabbage, same thing. Bottle gourd, French bean, okra. So, crop geometry, from the point of view of optimizing drip lines, we have moved now as an offshoot of that objective to reduce the cost of optimize the cost of drip system. We also could change the plant row spacing. Please understand, plant row spacing and plant to plant spacing is canopy driven. Canopy size. See, two rice seeds, two rice hills, you can have at 20 centimeter spacing. Two onion plants, you can have at 10 centimeter spacing because they are straight up. Their canopy doesn't spread. But you cannot grow two brinjal plants at 10 centimeter because it will have a flat umbrella canopy. So that knowledge is what helping the agronomist to decide this. So there are so many such streams of thinking, the thought process we put together to come up with a solution. That is why some of the spacings which we are recommending and our farmers are adopting happily because they found the results are good, are not available in textbooks of agronomy. Because textbooks are probably repeating in the textbook which was previously 20 years back it was there. They are not looking at other aspects of it. And I'm very sure many of the textbook crop spacing never probably considered a canopy adjustment, canopy space required for the crop. Sometimes you get too close so that the canopy will be shading each other. That itself will reduce the yield, whatever you do. Sometimes you get wider spacing because nobody thought of the canopy so narrow, like an onion canopy or a rice canopy, wheat canopy and all that, narrow. So what the planting was based on the textbook spacing. So what I'm trying to say is that there's a lot of changes. These are all flexible things. These are not sacrosanct. That you cannot, it is written in the book, so don't change it. I advise people to change it with knowledge, with your experience of the crop, and you must have a complete visualization of the crop when it is in full canopy. Then only this can be done. Because planting is done much earlier than the full canopy appears. So you cannot do a change later. You already decide to plant every 40 centimeter, thinking that the canopy will be about 40 centimeter diameter. That is why the 40 centimeter is given. 20 centimeter on this side, 20 centimeter on that side. That knowledge one should have it. Then all this is possible. Okay, so we have now come to a point for many crops, almost 65 crops, I think, except the tree crops, which are there also we made changes. We'll come to that totally different topic, high density plantation and all that. That's a totally different topic. I'm not going to touch it now. The main thing is that for other crops, non-tree crops, actually, you can change the spacing to accommodate based on its canopy space and the spread it actually requires to harvest maximum sunlight. Then drip irrigation, drip line spacing can be adjusted to do that. And here when you adjust it, you look at the soil, the lateral spread of the moisture. So they are connected. Now there is another thing. You have a dynamic placement. This is called, I call it a root spread. As the tree grows, see the left hand side, they are small, maybe 5 to 6 month old pomegranate plants on a sand dune. So the two drip lines which are assigned to them are closer. They must be placed closer because their root system is only spreading onto that level. But as they grow, I didn't get a mature thing to show the same. That's why I used another crop just to see the citrus crop on the right hand side. Even here, in the citrus also, when the citrus plants were small, these two drip lines were closer to the tree. But now, as I said, look at the canopy and put it within 1 foot from the edges of the canopy. That principle is followed maximum. And then you put the drip line. Two drip lines are far away from the tree now. That's the point here is, initially your spacing is closer, the drip line placement is closer to the tree. Later, as the tree grows, the canopy become bigger, you widen it. This is called the dynamic placement. You are not doing anything extra. You are only pulling out the drip lines to both sides. So you get the dynamic placement. Because this also has to be thought of it. It has to be implemented also. And that knowledge has to be passed on to the farmer so he himself can do it. He understands these things. Now we have an issue, intercrop on drip lines. So far we were talking about row crops and tree crops and some row crops which are closely planted row crops. We always thought of single crop. Mango alone, citrus alone, brinjal alone, ginger alone. But now there are a lot of systems, cropping systems are there in India. Especially the pulses are always grown as an intercrop. There's pigeon pea, you can see in the picture here, with another vegetable. Because the land equivalent ratio will be more than 1. That's the idea of intercropping. In other words, if you have a single crop, whatever value it produces for a hectare land, and that value plus 20%, plus 30% can be produced if you have two crops. Plus 50% will be very good actually. Because at a later stage, these crops may compete and the competition become least, then you choose the pairs, the crops. When the competition is highest, you don't choose them. You bring another partner crop. The partner crop should not reduce the yield so that you would get less than 1 as the total value of the land. That's the base. I'm just talking about a bit basics about intercropping anyway. Now here the point is, what type of drip irrigation system you can give? how the drip lines have to be aligned and assigned. See, here the issue is this: you have two unrelated crops, their crop season is different. Because, for example, in this case, the cabbage will be harvested in 4.5 months, 5 months. Finished. So, instead of cabbage, you can have even a watermelon. 75 days it will be harvested. So its crop duration, its different stages, all will be fitted into that 4 months or 75 days, whatever, based on the crop. While pigeon pea, and suppose this is a medium maturity pigeon pea, this goes to about 6 months. Or it is a early season pigeon pea, short season pigeon pea, even that goes to about 3, 4, 5 months, 4 months, like that. So the basic thing is that the crop stages, the flowering time, the fruiting time of the intercrop need not be the same time. Similarly, the requirement of nutrients, main problem is nutrient. Water can be, one can be slightly excess irrigated, the other one will get the ETP, somehow you can manage. But when the fertigation comes in, the requirement will be very different, both in terms of quantities of NPK as well as the splitting required, as well as what time you introduce potash, what time you pull out nitrogen, etc. will be different. Because if you continue to provide nitrogen for a crop like cabbage, it becomes very leafy. You do not get that round compact cabbage fruits. You don't get. So there are issues like that. One solution is this: when these were to be done, here the drip lines have to be separate. Number one. Number two, they have to be given on two separate submains, as if there are two individual crops, even though they are planted one after the other within the land. One row of cabbage, 2 rows of pigeon pea, then 1 row like that, or 2 rows of cabbage, or 2 rows of pigeon, whatever it is. So here either two submains, separate submains, or every lateral will have valves, open close valves at the submain point, so that when you are fertigating pigeon pea, you will close the valves to the lateral of the cabbages. Just an example, but that can be a bit difficult work-wise and can be a drudgery. People may forget, breaking of the valves will happen. So easiest is consider two submains, one submain for pigeon pea, one submain for the other crop. And then when you do fertigation, you open that particular valve going to the pigeon pea submain, which service, or the submain supplying to the cabbages. So you get the difference. So this is another. See, you started with a simple single crop, then you are coming to a bit more into crop geometry, then you are coming to double cropping, the two crops at the same time, intercropping, not double cropping, intercropping. So how you face with the drip line irrigation can be adjusted to all these situations. Now, for example, crop rotation on drip irrigation system, many of them which you have cotton, wheat. And sometimes sprinkler can be used for wheat, but sprinkler is not suitable for cotton. You get flower drop. So you cannot use that, and pollen wash. So sprinkler is out. It has to be a drip. Sugarcane drip. Potato cotton drip again, because cotton micro sprinkler is not is suitable for potato. It is not suitable for cotton. That's the same thing. Rice wheat, okay, you can have sprinkler system or drip system. A drip, of course, more water economy, higher yield and all that. Then you have potato, tobacco, maize systems. Actually, it is there. If you go to Andhra Pradesh, you will see that. 3 crops around. 1 drip system. Now, here I am bringing you to another aspect of this. So far, when you go to a farmer and as an engineer, you will ask, what is the crop? The crop is potatoes. Okay. What spacing, sir? So he will say his own. And if he comes back and talks to agronomist in the company, we will say, no, yeah, you tell the farmer he can do at this space. That also happens. This discussion, it's a 3-way discussion. But that stage is gone. Now, when you are giving a drip system to a farmer, the potato farmer, after potato, may be growing tobacco. It happens in some parts of Gujarat. Or he is growing maize. Many places it happens. And he cannot keep on changing drip for tobacco, drip for potato, drip for maize. The only thing which can change is the water requirement or the irrigation scheduling and the fertigation scheduling. That's all you can make change, because the crop to crop variation is there. And the total amount of fertilizer, etc. Fine. The schedule will also be different, because there are two different times of the season, two different crop factors. So schedule also will be different. But the system will be the same. In this case, one of the difficulty which comes usually is none of these. That is the spacing. Potato is planted at a certain spacing, and the drip lines are according to the potato crop. Tobacco is planted probably just at a different spacing. So the drip line versus crop row spacing may not match, but doesn't matter, because all the three are row crops. As long as you wet the strip of the land with the lateral spreading of the water, whatever, for which the drip lines are selected and spacing is decided, it matches all the three. It need not, as I said again, I go back, two chili plants need not have two drippers, one dripper each, just below the plant. That applies to here also. Only wetness should reach. So when you think about that, one drip system designed for potato, the only change you would make is actually when the tobacco comes or maize comes, is the schedules and advising the farmer different schedules, irrigation schedule, timing of irrigation, as well as fertilizer schedule. Then you have muskmelon. It's not musk, it's a spelling mistake, it is M-U-S-K. Musk, because of COVID, everything is now mask. Muskmelon and cotton. Sugarcane, wheat and sugarcane as a system, and drip. Cotton to onion. So these are I have listed them based on the actual crop rotations available in different parts of India. That's why they are real actually. They are not imaginary. The point being is that one drip system which is installed in the field can be used for following crops, rotation coming after the rotation. Then we can have crop optimizing water. The drip line is already there in the PGNP on the left side, and the melons planted here, and the peas planted at the bottom. But they have been put another cover. It's an add-on technology of mulching, which will help in conserving the moisture. Plus, it will reduce the weed incidence close to the crop. That's it. Here, the drip line will not make any change. In a way, it's good actually, because the surface evaporation is curtailed. You can even make some adjustments and lower the irrigation volumes you are applying. That's what the plus point about this is. This is again in a greenhouse where you have you have different types of, even without greenhouse you have potted plants. One dripper, how it is applying to one dripper, you can see on the drip line, the lateral line, there is a round thing as a dripper. It has a four-way, and then you are connecting with a microtube, and then each one will end. You can have this just a distributor, and at the end you will give the stake dripper for each of the tomato plant. Okay, this is another way of aligning drip irrigation system, drip line, for serving to more number of spaced plants. That this always happens in polyhouse. This also I should include to give a complete idea about the drip line placement. Now we are coming back to, or we are going to end as well as, but we are going to take up another totally different area, subsurface drip irrigation. We have talked about all this placement of drip lines, the crop geometry, everything, and how optimizing happens always when the drip line is on the surface. What will happen if they are in the, to make you understand that the drip lines, the left hand, and we have done quite a large area of subsurface drip for sugarcane especially. So I have put the left side is actually a paired row system of surface drip. The right hand side also is like that, but the only thing is that drip line is buried at certain maybe 10 centimeter below the surface soil to begin with the earthing up on top of that 10 centimeter. You may get at a later stage when the cane matures, you get the drip lines about 15, sometimes 20, 25 centimeter below the ground. Now, basic requirements of placement of drip laterals below specified depth. Here, one more thing comes in, the placement of lateral. That is, what depth you are going to place the drip line from the surface soil. This is to be thought of it. At the time of deep tillage depth or suitable depth to ensure repeated use of the laterals for many years, especially in a retunable situation of sugarcane. You are installing it and you can take 5, 6 or 7 crops based on the requirement, based on the soil health, based on the fertility you are adding. A lot of other considerations are there, agronomic considerations, which I am not going to talk about it. But the placement of lateral is important. Where the lateral should be. It should be a place where water moves and reaches the rhizosphere at the closest. Because it has a thread. The thread is the root entering back to the drip line through the drip hole, the orifice, for which we have treatments to prevent that happening. So one doesn't have to worry about it. We have been doing so many thousands of hectares under subsurface, and so far we haven't got any serious problem with the root entry, provided these prevention methods are carried out periodically. Now you do have, but because now the drip line is going to be installed at certain depth, the soil profile to the depth and below and above has to be tried to be made very uniform. That's why full disc ploughing one time, then a crosswise, then rotavator, so that clods are, because clods will not allow moisture spread. The passive spread of moisture which you saw laterally and vertical doesn't happen if there are clods. Then lateral laying machine operation has to be carried out. For sugarcane, for example, the normal spacing is lateral 6 feet or 4.55. Here, this is originally decided by the sugar mill and the area there, whatever they were following it. It can be even Pedro. But later, one more component has come to decide on the crop geometry, that is the harvester. Harvester blades are fixed. So the harvester blades, if it is fixed for 6 feet, then the planting has to be at 6 feet. Otherwise, it will miss the harvest. Anyway, that's what it is. So we looked at the different harvester machines available, and before deciding the lateral spacing, our topic is drip lateral spacing. There are 1.2 meter, 1.35 meter, then you have 1.5, 1.8. So first we have to check with the sugar mill which type of harvester they are having and what is the depth of the row spacing required. Based on the row spacing, you go back and do the drip line installation with the machine at a certain fixed depth. And in our case, because we looked at it very well, the movement of water and all that, we always put the dripper line above, as you can, than the sets. So you will have here slightly lifted above, and the two sets where the 2 rows of cane will be physically separated laterally as well as vertically a bit. Vertically they will be lower, because as the sets require moisture will move down by gravity, and so the germination will be better. This may not be a problem in clay and loamy soils, but in a sandy soil, very little capillary takes place. If the lateral happen to be below the sets may not get enough moisture for germination. That is the reason why it is kept always on the top. There are many people, actually many companies also, disagree with this. That is their science. We don't have anything to comment. We did not get a failure, while others got failure. And that is the proof of the success of this technology. Now we can see at a later stage how the drip line versus the root system, the depth and all that remains. Some pictures. Now this is another one, just a large one to show the drip line versus this is the only difference is that this is not in India. There they did plant only single row, but closer, single row per row drip lateral, and you can see the drip lateral spacing. Just want to show the depth of placement and all that, and the laterals will emit water closer to the and within the rhizosphere. Now subsurface is not only common in sugarcane, it is common in this is in Brazil, where the tea is coffee plants, young coffee plants with the surface strip, young coffee plants with the subsurface strip at a slightly away from that, but then the soil allows the moisture to move. See, the roots are there. The young plants have their roots closer even to the extent where the drip line is there. So that placement is made on one side. And see, at a later stage, you will see very huge trees of coffee bushes, but they are placed, unlike in India, they are placed very close, 1 meter between them, and then you have the subsurface drip line below that, and see plenty of root system. Roots, both fertilizer and water are injected. That is the correct placement of the thing. Here, you don't have a problem because there is no urgent, at least in sugarcane, after about 6 or 7 crops, you have to take out the line, remove it, and put, because you are plowing the land, preparing again, new planting has to take place. But in coffee, it's okay, years it can stay in this way. So this is a very successful system, and not so much done subsurface coffee in India. Main reason is that in India, coffee is not appearing in rows, neat and tidy rows. There, what we have the shade coffee with lots of trees in between, and there are certain proportion with the tree surface, tree canopy versus the coffee canopy and all that. But coffee is not at all planted, many places not planted in single rows. So that to put a system like this. And then the other thing is that trees are there, tall trees are there. In this sun coffee, it doesn't come, it is fully exposed to sun, and it's a totally different management of coffee. So the coffee also we do subsurface drip irrigation. So the placement, you can see the depth, how much it is. It cannot too deep there. When it is too deep, the heaviness of the soil will collapse the drip line also is possible. So there is an optimization of the depth and the placement based on the soil texture. Again, the dripper to dripper spacing, emissions, everything is decided. I try to cover a number of points, and which are actually this is not a theory, first talking and then later planning to implement it. It's the reverse actually. During implementations of drip irrigation systems for several crops, several types of soil, which is a fortunate thing to get that sort of experience from all over the world, we are now creating doable, repeatable theoretical steps. That's what it is now, how the placement should happen. So it's the reverse. The first, usually what happens is that we create the rules, then try to implement. Then there's the problems. Here, the rules are made only after observations from the field started coming, adjustments in the field to get the optimization done. For cost optimization, material optimization, matching with the soil, matching with the crop geometry, change the geometry, change the lateral. A lot of things have happened. Then, in a sense of that is what is I try to present in this webinar. Thank you.
Water is life. We all need clean water to live, to grow crops, to thrive. But there just isn't enough water or land to feed our hungry world. Unless we change the way we grow food. That's why millions of farmers are turning to Jain. Jain is totally integrated, totally innovative. Farmers helping farmers. The company logo reflects our holistic cycle of shared values. The sun, source of free renewable energy. Enhanced crops thanks to tissue culture plants and improved inputs. Water used sparingly and intelligently. The land protected and used wisely to deliver more. Jain has become a worldwide force in irrigation technology, the agri-value chain, and green energy solutions. Headquartered in Jalgaon, India, in just 2 generations, the company that started with 7,000 rupees has become a $1 billion organization, the world leader in agro-technology. Jain starts with detailed 3D designs and provides the widest range of irrigation products and solutions. In this remote part of the world where there is no electricity, Jain's solar-powered pumps provide on-demand irrigation through a variety of Jain pipes to irrigate the roots of plants produced in Jain's own fields and greenhouses. We pioneered the use of drip tapes for row crops with the innovative Chapin tape. Thanks to our micro irrigation systems and close work with farmers, we help them grow better produce that sells for more. We have even created a breakthrough technique to grow rice with drip irrigation. The result, better yields and better quality. Israel is known for bringing advanced irrigation to the world, and Nandan Jain led the way with integral drip line and sprinklers. Jain, total integration, total technological innovation, whether you farm 1 or 100,000 acres. No one offers a greater variety of products than Jain. On 5 continents, Jain is transforming the lives of farmers. Millions of farmers, 10,500 associates, more than 1,000 agro specialists, 30 production plants, sales in 116 countries, 7,000 dealers and distributors, global leaders in micro irrigation, mangrove processing, tissue culture plantlets, pioneers in solar agri pumping, producing 40,000 kilometers of drip tube every day, with annual revenues exceeding $1 billion and revenue growth of 1,400% in just 10 years. Why is Jain different? We are a global company that built our business on results, trust, constant innovation, and total integration. We are financially strong, enjoying steady, sustainable growth. We believe that you need to leave the world a better place than you found it. We believe in sustainability. We invest heavily in our people, our partners, and critically, our farmers. Food and energy security is tied to water security. But with today's technology, no one should ever go hungry. And every farmer, no matter how small or large, can produce more crop per drop. There is no need to fight wars over water, because if used wisely, we can make it last. Water is life, and at Jain, we are dedicated to improving life everywhere for everyone, now and in the future.